The simplest way of looking at integration is as the area under a curve. So here's our curve here, a function f of x as a function of x. And one way of thinking about the integral and as the area under the curve is to imagine that we divide this area up into approximately a collection of rectangles here. And all of these rectangles have got the same width, delta x, and they're approximately the right height, so that this collection of rectangles with their areas added up will give us approximately this total area under the curve. So we add up these areas, formally in a sum like this, and in the limit, as we make this delta x very small, this sum of all of these areas will give us the integral here. So it's the limit as delta x tends to 0, as this delta x becomes very small, of the area of all of these rectangles here. Notice in the integral that we have limits that we have put on here. We're integrating from x1 to x2, just as we see on the graph here. Now, the idea of area under a curve is all right if the curve is always above 0. We can extend this idea, however, to having the curve below 0 simply by using these parts as negative areas. So negative area doesn't usually mean anything, but it can mean something in the context of a curve like this. So when we come to work out the total area under here, these parts make a positive contribution and these parts make a negative contribution. So we still add everything up, some positive, some negative, to get our total integral here. And note incidentally that it's quite possible that because of this, the integral of some function that is basically non-zero nearly everywhere could still end up being 0 if it happened that the area underneath the line equaled the area above the horizontal line. Now obviously for this curve that's not the case. There's more positive area than there is negative, but we can certainly get a situation where our integral comes to 0. In our notation for integrals, mostly we write our integral sign on one side and our infinitesimal on the other, treating them sort of as if they were brackets round about the thing that we're going to integrate. And that's called the integrand. And for those of you who are into grammar, that comes from a Latin gerundive construction. And every time you see this, it means requiring to be. So integrand is requiring to be integrated. Alternatively, instead of putting everything we want to integrate in between the integral sign and the infinitesimal, we can have a notation where we don't do that and where we might have the integrand actually sitting outside of here. And the convention then is that if this variable is the same as the one in the infinitesimal, then everything with that variable in it is integrated. When we work with integrals, we mostly put limits round about them, so a definite lower limit and a definite upper limit. And an integral written that way and with those attributes is called a definite integral. So this is a definite integral because it's from x1 to x2. Sometimes, for formal purposes, we end up with an indefinite integral where we have not yet defined the limits. And that can be useful because sometimes we can get analytic results even though we have not yet defined the limits. So for example here, the integral of x squared dx without defining any limits is 1/3 x cubed. But we have an additional constant that we have to leave in here because we don't know what this is. And we don't know what this constant is because we have not put limits on this integral. And that constant, which at the moment here in this expression is still arbitrary, is called the constant of integration. One very important concept is the relation between integration and differentiation. Basically, they are inverse operations of one another. So specifically, if we take the integral from a to b of df by dx, the derivative of f with respect to x, then the result of that is f of b minus f of a. So the integration has undone the differentiation here and got us back to values of the function. Because we put limits on the integral, we have both of these values of the function here. But the concept is still that the integration has basically undone the differentiation. And this theorem, this statement here, is sometimes known as the fundamental theorem of calculus. Sometimes, but not very often, the integral is referred to as the antiderivative because of this relation of the inverse operation going on here.